Imagine trying to describe the universe without using numbers that never change. No fixed speed of light, no fixed Planck's constant, no fixed gravitational strength. Every measurement would shift beneath your feet. Physics, at its core, depends on stability. Constants are not just numbers written in textbooks, they're the anchors that allow physical law to exist at all. But what if they didn't exist? What if nature had no fixed scales? This question forces us to confront something unsettling. Are physical constants fundamental features of reality, or are they merely conveniences we invented to describe it? What is a physical constant? A physical constant is a quantity that has the same value everywhere, at all times, for all observers. Examples: speed of light, c, Planck's constant, h bar, gravitational constant, g, Boltzmann constant, k. These constants define limits, scales, transitions between regimes of physics. Without them, physics would not merely be harder, it would be undefined. This is a crucial point, especially for physicist audiences. Constants define what can exist, set maximums and minimums, determine which phenomena are possible. For example, without c, there is no universal speed limit. Without h bar, there is no quantum scale. Without g, mass would not curve spacetime. Constants are not decorations, they are structural beams of reality. The first thought experiment. Let's ask a dangerous question. What if physical laws existed, but the constants inside them were missing? You could still write equations, but those equations would have no meaning, because equations without constants have no scale. You wouldn't know how fast, how small, how massive, how energetic. Physics would lose its connection to measurement. Here is something subtle and profound. Constants do not tell us how nature behaves, they tell us how to compare things. Without constants, there is no small or large, no fast or slow, no strong or weak. Only relations without magnitude. Keep this in mind, it will matter later. Let's now begin removing constants, not all at once, but one by one. We'll start with the most familiar. Without the speed of light, c. If c did not exist as a universal constant, there would be no maximum speed. Cause and effect would lose a strict order. Space and time would no longer be unified. Relativity wouldn't merely be wrong, it would be impossible to formulate. Because c doesn't just limit speed, it defines the geometry of space-time itself. Without c, space and time become arbitrary. Observers cannot agree on causal order. Now loses universal meaning. Physics would fracture into observer-dependent realities with no shared structure. Without Planck's constant, h bar. Now remove h bar. This is even more devastating. Without h bar, there is no smallest unit of action, no quantum uncertainty, no wave-particle duality, no atoms as we know them. Quantum mechanics collapses into classical mechanics, but not smoothly. Instead, the concept of scale collapses. Why? Because h bar defines when classical intuition fails. Without it, there is no boundary between continuous and discrete. Energy levels blur into meaninglessness. Measurement loses fundamental limits. You wouldn't know whether nature is smooth or grainy. Without the gravitational constant, g. Now gravity. Without g, mass has no defined strength. Space-time curvature becomes arbitrary. There is no meaningful comparison between mass and geometry. Einstein's field equations still exist, but their physical interpretation vanishes. Mass would curve space-time. By how much? There would be no answer. At this point, something important becomes clear. Constants do not cause physical effects. They calibrate reality. They allow different physical quantities to speak the same language. Without constants, physics becomes dimensionless. Only ratios remain. Absolute predictions disappear. This leads us to a deeper realization. In a world without constants, physics would reduce to ratios, symmetries, dimensionless relationships. You could say, one thing is twice another, one process is faster than another, but never how much, how fast, or how strong in absolute terms. This is not hypothetical. Modern physics already hints at this. Physicists trust dimensionless constants more than dimensional ones. Examples: fine structure constant, approximately 1/137, mass ratios of particles, coupling strengths. Why? Because dimensionless numbers do not depend on units, are closer to pure structure, may reveal deeper laws. This suggests something radical. Maybe dimensional constants are not fundamental at all. Are constants merely human conventions? Could it be that c, h bar, and g are conversion factors, not features of reality, but bridges between human measurement systems? Some physicists argue exactly this. In natural units, c equals 1, h bar equals 1, g equals 1. The equations become simpler, almost elegant. This raises an uncomfortable possibility. Perhaps physics without constants is more fundamental, not less. A critical turning point. We have now reached the edge of basic understanding. From here onward, questions become deeper. Are constants emergent? Are they environmental? Could they vary? Is reality fundamentally scale-free? These questions lead us into quantum gravity, cosmology, information theory, anthropic reasoning. In advanced physics, something surprising happens. Physicists often erase constants. They write c equals 1, h bar equals 1, kb equals 1, sometimes even g equals 1. This is not laziness. It is not mathematical trickery. It is a philosophical statement. By setting constants to 1, physicists are saying these quantities are not fundamental. They are conversion factors between human-made units. Speed of light converts time into space. Planck's constant converts frequency into energy. Boltzmann's constant converts temperature into energy. Remove the conversion and the structure remains. What survives when constants disappear? When constants vanish from equations, what remains are symmetries, relationships, geometry, information flow. This suggests something profound. The deep structure of physics may be scale-free. Constants may merely tell us how big or how small, not what is happening. This idea appears repeatedly in modern theory. A crucial distinction, often missed. There are two types of constants. Dimensional constants depend on units, meters, seconds, kilograms. Dimensionless constants, pure numbers, no units. Physicists increasingly believe dimensional constants may be artifacts of description. Dimensionless constants may reflect true physical structure. This distinction will guide everything that follows. Reference: Duff, Okun, Veneziano, Trialogue on the Number of Fundamental Constants, 2002. What is scale invariance? A theory is scale invariant if the laws remain unchanged when all lengths, times, and energies are rescaled. In such a universe, there is no preferred size, no fundamental length, no absolute energy scale. Surprisingly, many physical laws are almost scale invariant. Examples: classical electromagnetism, certain quantum field theories at high energies, early universe cosmology. Why scale invariance is dangerous? If the universe were perfectly scale invariant, atoms would not have fixed sizes, stars could not stabilize, structures would collapse or expand endlessly. In other words, a universe without constants would be structureless or unstable. This suggests constants play a crucial role. They break scale invariance. They create hierarchies. They allow stable structures to form. In quantum field theory, something remarkable happens. Even if a theory starts without any scale, quantum effects can generate one. This is called dimensional transmutation. A famous example, quantum chromodynamics, QCD. QCD has no intrinsic length scale, yet it produces proton mass, nuclear size, confinement energy. The scale emerges dynamically. This strongly suggests constants may be emergent, not fundamental. Reference: Coleman and Weinberg, 1973, Gross, Wilczek, Pulitzer, Asymptotic Freedom, 1973. An emergent quantity is not fundamental, arises from deeper collective behavior. Temperature is emergent, pressure is emergent, entropy is emergent. Could constants be similar? Some physicists argue H may reflect quantum information limits, C may reflect causal structure, G may reflect space-time elasticity. Not fundamental ingredients, but effective descriptions. Gravity as an emergent phenomenon. Eric Verlande and others propose gravity may arise from entropy and information, not a fundamental force. In this view, G is not fundamental, it emerges from microscopic degrees of freedom. This idea remains controversial, but serious. Planck units combine constants, length, time, mass, energy. They represent where our current theories break down. But here's the key insight. Planck units are not measured, they are constructed. They signal our ignorance, not necessarily reality's smallest scale. In quantum gravity research, space-time itself may dissolve, constants may lose meaning entirely. Does space-time exist at the smallest scale? Approaches like loop quantum gravity, string theory, causal sets suggest space-time is not fundamental. Geometry emerges. Constants only arise after emergence. At that level, there may be no C, no H, no G, only relational structure. What if the most fundamental quantity is not energy, mass, length, or time, but information? In this view, constants encode limits on information transfer. C, maximum information speed, H, minimum information granularity, K, B, information entropy link. Physics becomes a theory of constraints on information. This idea connects black hole entropy, holographic principle, quantum information theory. At advanced levels of physics, constants stop being helpful. They begin to look like problems. This is not philosophical dissatisfaction, it is technical. The Standard Model contains 25 free parameters, masses, coupling strengths, mixing angles. These numbers are inserted, not derived. A deep discomfort exists among physicists. A fundamental theory should not require arbitrary numbers. If constants were truly fundamental, why so many? Why these values and not others? This is not aesthetic bias. It is a demand for explanatory closure. A theory with adjustable constants can fit any universe. This weakens it. In contrast, geometry, symmetry, topology, these explain why things must be the way they are, not merely how. Thus, constants increasingly appear as placeholders for missing understanding. In quantum field theory, coupling constants depend on energy scale, change with resolution, run under renormalization. This means constants are not fixed properties of reality, they are effective quantities dependent on scale. The fine structure constant changes with energy. The strong force weakens at high energy. This alone demolishes the naive idea of constants as eternal truths. Reference Peskin and Schroeder, An Introduction to Quantum Field Theory. The RG group describes how physics changes when we zoom in or out. RG flow reveals fixed points, universality, emergent simplicity. At fixed points, constants lose meaning. The theory becomes scale invariant. Only structure remains. This suggests constants are not fundamental. They are coordinates on theory space. Different microscopic systems can produce identical macroscopic behavior.
This happens in phase transitions, critical phenomena, condensed matter systems, meaning the universe forgets most of its constants. Only symmetry and dimensionality survive. This is devastating to the idea that constants define reality. No discussion of constants is honest without this. Quantum field theory predicts a vacuum energy 120 orders of magnitude larger than observed. This is not a small error. It is the largest discrepancy in science. The cosmological constant appears tiny, yet dominates the universe's fate. Why is it not zero? Why is it not enormous? No known principle explains this. If constants were fundamental, vacuum energy should be calculable, predictable, stable. It is none of these. This strongly suggests our understanding of constants is fundamentally incomplete. This topic is often abused. We will not abuse this. The weak anthropic principle states observed constants must allow observers to exist. This is not mystical. It is a selection effect, but it explains nothing dynamically. In eternal inflation and string theory, constants may vary across regions. Each region realizes different effective physics. Our universe may simply be a stable point in a vast parameter landscape. This does not explain constants, it replaces explanation with statistics. Many physicists find this deeply unsatisfying. Reference Susskind, The Cosmic Landscape, Tegmark, Our Mathematical Universe. Modern mathematical physics increasingly uses category theory, topology, algebraic structures. These frameworks do not rely on numerical constants. They describe relationships directly.
This aligns with a radical idea. Reality is relational, not numerical. Numbers appear only when measurement enters. At the deepest level, laws may be consistency conditions, symmetry constraints, information bounds. Constants then appear as boundary conditions, not laws themselves. This reframes physics entirely. There exists a maximum information content for a region of space. This bound involves energy, area, and entropy. Constants appear, but only to convert units. The bound itself is geometric and informational. Black holes do not remember particle types, do not remember coupling constants. Only mass, charge, and angular momentum remain. This is not metaphorical. It suggests that at fundamental limits, constants are forgotten. Reference: Hawking, Black Hole Radiation, 1975. All constants assume time, measurement, comparison, but quantum gravity suggests time may not exist fundamentally, only correlations do. If time disappears, constants lose definition. Constant becomes meaningless. Reference: Ravelli, The Order of Time. Physics today stands in a strange place. We have equations that work perfectly, constants we cannot explain, predictions that depend on numbers we do not understand. This is not failure, it is diagnosis. It suggests we are describing shadows, not foundations. Constants may be emergent, environmental, informational, or placeholders for deeper structure, but they are almost certainly not fundamental in the way we once believed. Why a constant-free theory can still produce constants? At first glance, this sounds contradictory. If a theory has no constants, how can constants ever appear? The answer lies in symmetry breaking, coarse graining, and observational perspective. At the deepest level, a theory may have no preferred scale, no preferred unit, no preferred magnitude. Such a theory is maximally symmetric, but maximal symmetry is unobservable. To observe anything, symmetry must be broken, distinctions must arise, comparisons must become possible. Constants may be fossils of broken symmetry. Example, spontaneous symmetry breaking. In particle physics, laws are symmetric, solutions are not. The Higgs field introduces mass, sets energy scales, creates numerical values. The constants we observe may arise the same way, not from laws, but from the state of the universe. Before measurement, there are relations, correlations, constraints, but no numerical values. Numbers enter physics only when an observer defines a standard, a comparison is made, a ratio is fixed. Constants may be properties of measurement frameworks, not reality itself. Take any constant, c. C compares space to time. H bar
H-bar compares frequency to energy. KB compares entropy to energy. They translate between descriptions. This strongly supports the view. Constants arise because observers insist on comparing unlike quantities. Without observers, no translation, no constants, only structure.
Why observers cannot exist in a scale-free world? A perfectly scale-free universe has no stable atoms, no fixed chemistry, no persistent structures. Observers require memory, stability, and irreversibility. All of these demand fixed scales. Thus, a universe that contains observers must generate constants. This is not anthropic hand-waving, it is a thermodynamic necessity. Entropy introduces irreversibility, arrow of time, and preferred coarse graining. The moment entropy matters, microscopic symmetry is lost. Macroscopic constants appear. This links constants, entropy, and observation. They are not separate ideas. Coarse graining means ignoring microscopic detail, describing collective behavior. When you coarse grain, new quantities appear, new constants emerge, new laws replace old ones. Temperature is born this way. Pressure is born this way. Viscosity is born this way. Constants may be no different. At different scales, different constants matter, different laws dominate. Example, atomic physics, H-bar, relativity, C, gravity, G, thermodynamics, KB. This suggests constants label levels of description, not ultimate reality. Physicists once believed deeper layers explain everything above, but modern physics shows higher-level laws are autonomous. Constants appear at each level. Reduction does not eliminate them. This is why condensed matter physicists speak of emergent laws that do not reduce. Constants belong to this category. Reality may be a hierarchy of descriptions, each with its own constants, none absolutely fundamental. This reframes the original question. To do physics, you must distinguish this from that, before from after, here from there. Distinction requires boundaries, thresholds, scales. Constants create these thresholds. Without them, reality may exist but be inexpressible. A constant-free theory may exist mathematically, exist structurally, but contain no statements expressible as measurements. Physics may fall silent there. Physicists dislike unexplained constants, yet cannot eliminate them. Why? Because constants anchor experience, enable prediction, stabilize description. They may not be fundamental, but they are indispensable. This tension defines modern theoretical physics. We now stand at a point where a universe without constants is conceivable, but not observable, not measurable, not describable in physical language. Constants may be emergent, observer-dependent, scale-dependent, informational. Yet once they appear, they dominate everything. We are not done. Modern mathematics contains vast domains that do not rely on numbers, do not use magnitudes, do not measure anything. Examples: topology, category theory, graph theory, order theory. These frameworks describe relations, connections, transformations. They are perfectly consistent, but physics cannot remain there for long. Why? Because physics is not just structure, it is structure plus comparison. The moment physics asks how much, how fast, how likely, numbers must enter. Constants may be the entry points of number into structure. If reality is continuous, fields take infinitely many values, fluctuations exist at all scales, divergences appear immediately. To control infinities, physics introduces cutoffs, normalization scales, reference values. These become constants. Without them, predictions diverge, equations lose meaning, measurement collapses. Thus, Constants may be required to make continuous reality mathematically manageable. Reference: Renormalization Theory. Zinn Justin, Quantum Field Theory and Critical Phenomena. In renormalization group flow, most parameters change with scale. Some combinations remain invariant. These invariants act like constants. They are not inputs, they are attractors. This means constants may be inevitable outcomes of consistency, not arbitrary choices. If fixed points are universal, many starting conditions converge. Detailed differences are erased. Similar constants appear. This weakens the idea that constants are random. They may be structurally selected. We now ask a dangerous question. Are constants features of reality or features of what can be known? Any physical theory uses mathematical language, relies on axioms, assumes standards of comparison. Constants may encode where description breaks down, where explanation must stop. They are epistemic scars. Just as mathematics has incompleteness, physics may have irreducible constants, not because nature is arbitrary, but because self-description is limited. Observers are physical, evolve in time, require stability. They can only exist in regimes where constants appear fixed, laws are reliable, fluctuations are suppressed. Thus, observers filter reality. They experience constants as immutable because only such regions permit observation. If constants varied rapidly, atoms destabilize, chemistry fails, memory collapses. Any observer detecting variation would not survive long enough to report it. This is not circular reasoning, it is dynamical selection. Just as matter has solid, liquid, gas, plasma, reality itself may have different physical phases, different effective constants, different dominant descriptions. Our universe may be in a low-energy, symmetry-broken phase where constants crystallize. During phase transitions, values freeze, fluctuations collapse, symmetry breaks. Cosmological phase transitions may have fixed coupling strengths, set mass scales, determined constants. Once frozen, they remain stable.
Reference: Kibble mechanism. Early universe cosmology texts. A final theory might explain only why constants exist, not their values. It may tell us why constants must appear, why they are stable, why they allow complexity, but not why this number and not another nearby one. This may be the natural stopping point of explanation. Physics may eventually explain relationships, constraints, symmetries. Numbers may remain as initial conditions, boundary selections, historical accidents. This does not weaken physics, it clarifies its limits. What would physics look like without constants? It would look like pure structure, pure relation, pure possibility. But the moment observation occurs, entropy matters, memory forms, constants must appear. Not because nature prefers numbers, but because description demands them. One of the oldest unanswered questions in physics is this: is reality fundamentally continuous or discrete? This question is not academic. It determines whether constants are optional or unavoidable. In a perfectly continuous universe, there is no smallest length, no smallest time, no smallest energy. Everything can be divided endlessly. But such a universe immediately faces problems: infinities in field theories, divergences in energy, loss of predictive control. To make sense of a continuum, physics must introduce cutoffs, regularization, reference scales. These scales become constants, not because nature insists, but because description collapses without them. Suppose instead that reality is discrete. Then physics must specify spacing, step size, transition thresholds. These too are constants. Thus, whether reality is continuous or discrete, constants appear as soon as structure becomes describable. Imagine a non-human intelligence, different senses, different biology, different mathematics. Would it discover the same constants? The answer is subtle. Not the same units, not the same numbers, but the same dimensionless relationships. This suggests Constants are not human inventions, but observer-dependent expressions of deeper structure. Any intelligence that measures, predicts, remembers must introduce stable reference points. Those reference points appear as constants. Intelligence requires memory stability, repeatability, error correction. All of these require thresholds, tolerances, invariance. A world with no constants cannot support cognition, not human, not alien, not artificial.
After all this depth, something becomes clear. Physicists keep asking, why these constants? Why not others? Why any at all? Because constants sit at the boundary between explanation and existence. They are where law meets history, structure meets accident, mathematics meets reality. This is why the question never goes away. Physics without constants would be relational, scale-free, timeless, structure only. It would be closer to pure mathematics than empirical science. 36.2. Why such physics cannot be observed. Because observation requires comparison, scale, memory, irreversibility, all of which introduce constants. Thus, a constant-free physics may exist, but it cannot be experienced. This is important to say clearly. Constants are not embarrassments, placeholders for ignorance, signs of incomplete physics. They are the price paid for having a universe that can be described from within. A universe that explains itself perfectly may be one that cannot be inhabited. What would physics look like without constants? It would look like pure relation, unbroken symmetry, no scale, no arrow, no observers. In such a universe, nothing is wrong, but nothing can be said. Constants do not answer questions. They allow questions to exist. They allow atoms to persist, clocks to tick, energy to flow, information to accumulate. They do not tell us why reality exists, but they tell us how reality becomes intelligible.
Perhaps the deepest lesson is not that constants are mysterious. It is that a universe without constants may be more perfect, but a universe with constants is the only one that can be understood. Physics does not seek perfection, it seeks comprehensibility. And constants, unexplained, stubborn, unavoidable, are the quiet cost of that comprehensibility.